Now I'm going to start combining inductors, capacitors, and resistors to make an overall electrical circuit. Our first step towards doing this are going to be what are called first-order systems, or if it's electrical circuits, first-order circuits. First-order systems, as you might guess from the name, are governed by a first-order differential equation. So there is a derivative in the governing equation that relates the output to the input, but there is only a single derivative term. It is only a first-order derivative. Now, one byproduct of this is that first-order systems will have a single energy storage element. So if you're dealing specifically with first-order electrical circuits, they will have a single capacitor or a single inductor. There's a slight generalization to that. Okay? As we've seen before, series and parallel combinations of capacitors and inductors can be simplified into a single capacitance or inductance. So what they really have is one single equivalent capacitor or a single equivalent inductor. So if there are two capacitors in a first-order circuit, they are either in parallel or series. You can replace those with a single equivalent capacitance. Likewise for inductors. Okay, recall that we kind of like our system-level viewpoint of these circuits. We have some system, which for us will be an electrical circuit. It has some input, which I will typically denote in general as U of t, and some output, which I will denote as Y of t. Now, for a first-order circuit or system, it will be governed by a first-order differential equation. In general, the differential equation relating Y of t to U of t will look like this. There is a single derivative term. I have some unknown constant A1 times the derivative of the output with respect to time, which plus another constant A0 times Y itself is equal to the input. I can always write my first-order differential equation in this form. Now, as I said earlier, a couple of lectures ago, the output for systems which store energy is dependent upon the previous state of the system. That state is described by what is called the initial condition. I need to know what the value of Y is at some time in order to be able to solve this differential equation. So I need to be given Y at some time t equals t0, and that time is fairly arbitrary. As long as I know it at some time and I know U of t for all later times, I can find Y of t for all later times, assuming that A1 and A0 are constants. This is going to be some number Y0. Okay, so I have a governing differential equation in a very general form. I have some known initial condition, a value of the output at some time. Now, as I said way back in the dim and distant past in Lecture 1, this class is best taken in conjunction with a differential equations class, or having had a differential equations class already. Now, I want to give a brief overview of how these equations, differential equations, are solved, but I'm not going to get into any gory details about this. I'll try to give you a feeling for what's happening and hopefully refresh your memory as to what's going on. When I solve a differential equation, my solution has two parts. It is typically called y sub h of t, which is the homogeneous solution, and y sub p of t, which is the particular solution. The homogeneous solution contains the part of the system's response which is due to the initial conditions. Remember that I said that the response of the system is based on the current state of the system. Okay, you have to know the state of the system in order to determine what the system is going to do after that time. Y sub h of t tells me what that is. Y sub p of t, the particular solution, is due to the particular forcing function. Okay, U of t can be any function. Okay, whatever it is going to affect your solution. It affects the solution through the particular solution. Okay, so essentially we've decomposed our solution into two parts, then we sum those up. Okay, the part of the solution that's due to the current state and the part of the solution that's due to the input. We can sum these up because this is only for linear systems. Remember, I said we were talking only about linear, ordinary differential equations with constant coefficients in this class. Since these differential equations are going to be linear for us, this superposition works. We can look at the system state response and the system input response separately and then superimpose them. Let's take a quick look at the homogeneous solution and a few concepts that will be important to us relative to this. Okay? In lecture 14, I said that a dynamic system's response depends upon the system's state at previous times. The initial condition contains the state at some previous time. The homogeneous solution is the system's response to those initial conditions. It contains the part of the solution that is due to this system's state at previous times. Okay. The input to determine the homogeneous solution is assumed to be 0. Okay? You're assuming that you're not applying any input. You're starting up the system from a set of initial conditions and just letting it respond. Some nomenclature. The homogeneous response is sometimes called the unforced response, the natural response, or the zero input response. It's unforced term. Generally, U of t is referred to as the forcing function. If it's 0, the system is said to be unforced. The zero input response, that nomenclature is because the input is 0. I will tend to refer to it as the natural response. Okay, it's how the system wants to respond in the absence of you driving it with anything. So this will generally tend to be my preferred nomenclature. Any of the above are fine. One important thing, all physical systems dissipate energy. Okay, the second law of thermodynamics tells us that this has to be true. We can't build a perpetual motion machine. If all systems dissipate energy, and if I'm not providing any energy to the system from an external source with U of t, this homogeneous solution has to decay to 0 as t goes to infinity. This is important. We'll need to remember that when we're looking at the particular solution next. Okay, now let's talk a little bit about the particular solution. Okay, the particular solution is the response of the system only to the input. Okay, we're assuming that any initial conditions are 0, just driving the system with the input. Now, it turns out that the form of the particular solution is dictated by the form of the forcing function. Okay? The form of U of t will tell me what the form of y sub p of t is. Okay? For example, if I put in a sinusoid into the system, the output will be a sinusoid. If I put in a constant value, the output will be a constant value. For the particular solution part, that is not pertaining to the homogeneous or the natural response. Now, since we're looking at the response to a forcing function, this is sometimes called the forced response. The state is tending to be referred to as what the information is that's contained by the initial conditions. So another common terminology is that this is the zero state response. The state or the initial conditions of the system are taken to be 0. I will tend to default to this terminology. I'll call the particular solution, for the most part, the forced response. Remember that the homogeneous solution goes to 0 as t goes to infinity. The overall solution, y of t, is the sum of the particular solution plus the homogeneous solution. As t goes to infinity, this guy goes away, so y of t becomes y sub p of t as t goes to infinity. So if I let t go to infinity, the only thing that's left over is the particular solution. That is an approach that we will use to determine what y sub p of t is later on. Okay, previously we used a qualitative example of heating a frying pan to illustrate some of the points relative to dynamic systems. I want to keep doing that. Okay, I'm going to take this same example again and try to look at my homogeneous or natural response and my particular response or my forced response in terms of physically what's going on in here. Okay, so it's an example that we have some intuitive feeling for how it's going to behave. I want to put these mathematical concepts in the context of that intuitive understanding before we get into the mathematics themselves. We'll develop the mathematics when we start looking at first-order electrical circuits. So as a refresher, we have some mass, okay, the mass of our frying pan with some specific heat, C sub P, and it is at some temperature, T sub B. I can have an input heat, Qn, that's applied to this frying pan, and the difference in temperature, T sub B, and the ambient temperature will result in some heat dissipation, Q out. So looking at this from a system level standpoint, our system is the frying pan itself, our input is the heat we're applying to the frying pan, and our output is taken as the frying pan's temperature, T sub B, which typically will be a function of time. Now the natural response, or the homogeneous solution, is going to be due to some initial temperature of the pan with no heat being applied to the pan. So graphically we looked at this before, where if we had some initial temperature, and if we didn't apply any heat to the pan, so if I heat up my pan and I remove the heat, I get to some initial temperature. The temperature of the pan without any heat added to it will decay exponentially to whatever the ambient room temperature is. Okay, this is our exponentially decaying function. Now the particular solution, or the forced response, is due to the input alone. It doesn't take into account any initial temperature of the pan. So Y sub P is a constant as long as my input heat is constant. So our previous example, we just applied a constant heat to the frying pan and we looked at what we expected the frying pan temperature to do. If the heat input is constant, the particular solution has to be a constant value. So my particular solution is just going to be a number. These two solutions need to be superimposed to get the overall response. Now, superposition doesn't necessarily mean just adding them up. It's a linear combination. You can scale and add them. You can scale and subtract them. You can do any linear mathematical operations between these two in order to get the result. And when we looked at this before, we said, okay, if I have the frying pan at some initial temperature and I suddenly start applying a constant heat input to it, the temperature of the pan is going to come up exponentially and it will eventually become constant when the heat into the pan and the heat out of the pan balance each other out. So what I've got is an initial condition, okay, my initial state, which is denoted by the initial temperature. Once the natural response or the homogeneous solution dies out, my final temperature is the particular solution. It will just be a constant number since my heat input is constant. This exponential change between the initial and the final value is due to my natural or my homogeneous solution. Now, a couple of other terminology things. There is contained in this what is called a transient response and a steady state response. The transient response is when things are changing and the natural response is showing up in your overall response. Okay, the transient response contains both the response to the initial conditions and the specific input that you're applying. Once the natural response or the homogeneous solution has died out, you get your steady state response. Okay, the steady state response is really just the particular solution. Keep those terms in mind as well. We will be using them later on too. Now let's start looking at some responses of electrical circuits. Okay, And the first thing we're going to look at is an RC circuit. As I mentioned in the introduction to this lecture, an RC circuit contains a resistor and a single capacitor. Okay? The easiest case for now is the natural response, so let's determine the natural response of an RC circuit. I first want to just kind of give a quick overview of what we can expect out of this problem. So the way we've set this up is we have a capacitor here with some switch which connects it to a resistor. For times less than 0, this switch is open. Okay, there is no current flowing through the resistor from the capacitor. When time t equals 0, we suddenly snap this switch shut. Now we can start flowing current from the capacitor to the resistor. The resistor will start dissipating energy. So, first thing to note is that we have no power sources. There's no external power supplied to this system. Okay? The input u of t is 0. That's why this is a natural response. What we're going to be finding is the homogeneous solution to this system. Any response of the circuit is going to be due to energy initially stored in the capacitor. So before this switch closes, what we're going to do is provide some non-zero voltage across this capacitor. So V at t equals 0 is some initial voltage V sub 0. So we're going to store some initial energy in this capacitor sort of magically. We just claim that there's a voltage across the capacitor. We don't know where it came from. We don't care. Okay. Then, once we close this switch, we will start flowing current into the resistor. The resistor dissipates energy. So the initial energy that's stored in the capacitor will be dissipated by the resistor. If we look at this voltage as a function of time, it should start out at V0 when time t is equal to 0 and decay exponentially down to 0, kind of like the natural response of our frying pan. Okay, now let's actually determine the response of this circuit to this change in switch position. So we'll mathematically determine the natural response of this RC circuit. So our problem statement is to find V of t, the voltage across the capacitor, as a function of time for times greater than 0, so after the switch has been closed. We're going to claim that the initial condition which we have to be given is that the voltage across the capacitor before the switch moves is V is equal to V0. Notice this nomenclature, V of 0 minus. The minus indicates that this is an infinitesimal amount of time before t equals 0. So it's just before I switch this switch, this V of t is equal to V sub 0. Now what we're actually interested in is the voltage for times greater than 0. So the first thing we need to find out is our initial condition. Remember back when I talked about capacitors, I said there were a couple of extremely important things about them. One of which is if everything in the circuit is constant, the capacitor behaves as an open circuit. The other item was that you cannot change the voltage across the capacitor suddenly. So if I know the voltage across the capacitor just before I switch this switch, I know the voltage across the capacitor just after I switch the switch over. So V at t equals 0 plus, just immediately, infinitesimally after I close this switch, has to be equal to V at t equals 0 minus, which is V0. This is because you can't change voltage across a capacitor suddenly. Okay, so in order to get our solution, we'll need an initial condition, which we now have. We also need the governing differential equation for the circuit. So once we've got this, now let's take a look at the circuit itself for times t greater than 0. So for t greater than 0, the circuit looks like this. I have a capacitance C. This switch is closed. I have a resistor R. And my voltage across the capacitor is V of t. Now I need to invoke my voltage-current relationships. Okay, the current through this resistor, I sub R, by Ohm's law, is just V of T over R. Notice that my current is entering the positive voltage node. My current through the capacitor, I sub C, is equal to C dV by dt. Okay, the voltage-current relationship for a capacitor. If I do KCL at this upper terminal, I say that I sub C plus I sub R is equal to 0. Therefore, C dV by dt plus V over R is equal to 0. Simplifying this, if I divide through by C, my governing differential equation is going to become dV by dt plus 1 over RC times V is equal to 0. Note that I have no power source, I have no input. U of t in this expression is 0. I'm finding the homogeneous solution or the natural solution only. Now, in the previous slide, I determined the governing differential equation, dV by dt plus 1 over RC times V is equal to 0, and the initial condition, V at t equals 0 plus, just after the switch is closed, is equal to V0. Once I've got the governing differential equation and the initial condition, this can be solved to determine V of t. To solve this, let's take this guy here and separate variables. I'm going to group all the t's on one side and all the v's on the other side. So this can be written as dV by dt is equal to minus 1 over RC times V. If I multiply both sides by dt and divide both sides by V, I get dV over V is equal to minus 1 over RC times dt. I can integrate both sides of this. If I integrate dV over V is equal to minus 1 over RC times the integral of dt, I start my integration process at t equals 0. Since I want this as a function of time, I integrate to t equals t. The voltage at t equals 0 is just V of 0, which I've said is capital V sub 0. The voltage at time t is what I want to find, which is just V of t. Let me do this integration. Integral of dV over V is the natural log of V, evaluated from V0 to V of t. That's equal to minus 1 over RC, evaluated between 0 and t, which is minus t over RC. Natural log of V becomes natural log of V of t minus natural log of V0 is equal to minus t over RC. This can be rewritten as the natural log of the ratio of V of t over V0 by the rules of logarithms is equal to minus t over RC. Now, to get rid of this nasty natural log, I can take e to both sides of this. Coming back over to this side, V of t over V0 is equal to e to the minus t over RC. So V of t is equal to V0 e to the minus t over RC. That is my final solution. If I plot this, I start out at some voltage V0. And this decays exponentially to 0, and it has a time constant tau equal to RC, At tau, I get to 0.368 of V0. So as we expect, we start out with a voltage of V0 that decays exponentially to 0. The resistance and the capacitance dictate the time constant of the function tau. Okay, let me briefly recap our results for the natural response of an RC circuit. As we found previously, the voltage across the capacitor for this circuit is the initial voltage times e to the minus t over RC. The shape of the curve looks like this. Now, previously we introduced exponential functions in the form f of t is equal to some number times e to the minus t over tau, where tau is the time constant. What happens is that the value of this function decreases by 63.2% every tau seconds. So we can take this guy here and put it in this form by writing v of t as v0 e to the minus t over tau, where tau is r times c. So essentially, the resistance and the capacitance together are setting the rate at which your voltage decays. Okay? So if I keep my capacitance constant and increase my resistance, my time constant goes up. Okay? Likewise, if I keep my resistance constant and increase my capacitance, the time constant goes up. So tau is increasing in this direction. So what's happening as the capacitance goes up, I'm storing more and more energy. Okay? The more energy I have in the capacitor relative to the amount of resistance I have, the longer it takes for that energy to decay away. Likewise, as the resistance goes up, the less current I'm flowing through the resistor dissipates energy more slowly. So if the resistance goes up without changing the capacitance, the time constant increases. If I change resistance and capacitance inversely to one another, I don't change the time constant at all. If I double my resistance and halve my capacitance, this response looks exactly the same as it would have done before. Okay, so keep in mind the resistance and the capacitance together are dictating the rate at which the natural response will decay. Let's do another example of an RC circuit natural response. I have this circuit here with two capacitors in it placed in parallel. Before time t equals 0, I have this switch in its closed position, so this source is applied to this circuit. So before t equals 0, I'm actually applying energy to this circuit that will result in some energy being stored in these capacitors before I open this switch. Now, after I open this switch, this initial energy in these capacitors will dissipate through these resistors. So after I open this switch, the circuit over here will be doing a natural response. It will no longer be forced. Okay, we're going to force the response in order to get up to the initial voltage. Then when we open this, we just strictly have some kind of RC network. So we want to find the voltage across this resistor, or equivalently the voltage across these capacitors, since they're all in parallel, as a function of time for t greater than 0. So we need to do two things. We need to find some initial voltage across these capacitors, and we need to determine the differential equation governing this circuit. We have two capacitors. We don't necessarily know how to deal with situations where we have multiple energy storage elements, except in this case our two capacitors are in parallel. Okay? So parallel capacitors can be combined by adding the capacitances together. So these two capacitances become a single 1 millifarad capacitance, because capacitors in parallel add directly. Okay? So for times t greater than 0, I can redraw this circuit as a open circuit with a 100 ohm resistor, a 200 ohm resistor, and a single equivalent 1 millifarad capacitor. Okay? This is an open circuit, so there is no current going through this resistor. The voltage difference across here is 0. This circuit is equivalent to this 200 ohm resistor in parallel with a 1 millifarad capacitor, and we want to find V of t. This is exactly the problem we did last time, except that we actually have numbers for the capacitance and the resistance. So this is the circuit we're going to be analyzing. We also need to determine the initial conditions. Before this switch is opened, everything in this circuit is constant, assuming that the switch has been closed for a long, long time. Okay, so before we have this open, everything's constant. We claim that if everything is constant in a circuit, the capacitors look like open circuits. So I can redraw this circuit as a 9-volt source with a 100 ohm resistor and a 200 ohm resistor. The capacitors simply behave as open circuits. They do not affect anything. So this is V at 0 minus. This just looks like a voltage divider. So before I open this switch, V at 0 minus is just 200 over the total resistance, 200 over 300 times 9 volts, which is just 6 volts. Since I cannot change my voltage across capacitors suddenly, okay, when I suddenly open this switch at V equals 0 plus, this voltage will not change. My initial voltage when this switch opens is going to be 6 volts. Note carefully what we've done here. When we're determining the initial conditions, we've used our two properties of capacitors. One, that when everything is constant, capacitors can be replaced with open circuits. Second, I cannot change the voltage across a capacitor suddenly. That gives me my initial conditions. On the next slide, we'll take this circuit with these initial conditions and analyze it to determine V of t. Okay, as we found out on the previous slide, this whole circuit, after the switch is open and the source is removed from the circuit, simplifies down to a single resistance with a single capacitance. This looks exactly like our previous natural response example. We found out there that V of t is equal to V0 e to the minus t over RC for time greater than 0. We don't really need to go through and rederive that. We just need numbers for V0, R, and C. V0, we already found out was 6 volts. That's our initial condition. R is 200 ohms and C is 1 times 10 to the minus 3rd farads. So RC is 200 times 1 times 10 to the minus 3rd, which is 0.2. So V of t is equal to 6 e to the minus 5t volts for times greater than 0. We've got what we originally set out to get. This concludes lecture 16. In this lecture, we talked about the voltage-current relationships for inductors. We also talked about combining series and parallel combinations of inductors. So now we have the governing equations for our two energy storage elements, capacitors and inductors. We could go ahead and start putting those together in electrical circuits. So the first thing that we did were first-order electrical circuits, and we determined the natural response of an RC circuit, which consists of a single equivalent resistor and a single equivalent capacitor. Next time around, we'll talk more about first-order systems, and we'll do some more natural response examples. We will include the natural responses of what are called RL circuits, consisting of a single resistor and a single inductor.